Hello everyone, welcome back to the channel, and today we are discussing another Leetcode medium problem, course schedule 2. Now this problem is a continuation from my previous video which was course schedule. So you can definitely go check that out because I discussed two important graph algorithms in that video which we're going to use today as well. About this problem also uses two very important graph algorithms which are asked by many companies regularly. This question directly itself is also an interview problem which has been asked previously in companies like SAP, Paytm, Flipkart, Amazon, Microsoft, and the list just goes on. So if you like today's video, don't forget to leave a like and subscribe to the channel and check out other videos as well. In the description below, you'll find the link to course schedule 1 as well as the entire playlist. So you can definitely check that out if you're preparing for technical interviews. So without further ado, let's move on and discuss the problem. So you can pause on the video and read out the question statement once. Even if you don't read it, I'm just going to explain it. So I hope that you've read the question statement, and let's move on and let's try and understand what the question is saying. So what the question says is similar to what we did in course schedule 1, is that you're going to be given a list of some courses, which suppose this is one course, right? And its prerequisite is this course. So it is going to be a directed graph, right? And suppose you need to take both of these courses to complete this course. So it's going to be given a directed graph. How we reach to that is in course schedule 1. So I'm mentioning it again that you should definitely watch that video so that the understanding towards this video is better. So we'll be given a graph and we have to return the order in which we should take all the courses. So let's start discussing how we're going to do this. So the algorithm that we're going to use is, you must have heard of it, topological sort. Topological sort. But only topological sort is not enough. You need something else as well. We'll just get to it in a moment. Let's just first discuss what topological sorting is. So what topological sort does is suppose that you're given a graph like this, right? And let's number them. Let's number them 1, 2, 3, and 4. So what does this graph represent is that for taking up course number 4, you must have done course number 2 as well as course number 3, since there is a directed edge from 2 and 3 both to 4. Similarly, for doing course number 2, you must have done course number 1, and for doing course number 3, you must have done course number 1. So topological sort returns the order in which you have to take up these courses so as to complete all the courses. So let's discuss in this graph. So first of all, you need to take course number 1. So I'll write it down here. Now next, you can take either course number 2 or course number 3. So I'll just take course number 2. Now from 2, you cannot take 4 because for 4, you also need to take up course number 3. So first I take up course number 3 and then finally I reach to course number 4. Right. So this is what the return value for my topological sort is going to be, that this is the order in which you can take up courses. You could have also switched 2 and 3, and that is also a fine order. So that's what topological sort is. Now let's discuss how topological sort works. Right. So there are of course two ways to do so, the DFS way and the BFS way. Right. So I'm just going to quickly brief you about the BFS way and then move on to the DFS way. So in BFS way, what you do is you mark in degrees for each node. So let's start marking in degree. The in degree for this node is 0. For this node is 1. For this node is also 1. And for this node, it's 2. So what you do is that first you take a stack and push all the nodes which have in degree 0. So only one node has in degree 0. So I push it in. Now you pop this element from the stack. So let's pop it. And what you do is that you take it in the order. So 1 is now in the order, right? And you decrement the value of in degrees of its neighboring nodes. So its neighboring nodes are 2 and 3. So I decrement their value. And again, similar, if their in degree becomes 0, you push them into the stack. So I push 2 and I push 3, right? So is any further node getting decreased? No. So now I pop the first element from the stack. I pop 3 from the stack and I take it in my order and decrease its neighboring nodes in degree by 1. So 2 becomes 1, right? So will this 4 be pushed into stack? No. But now 2 is the top element. So you push it out and take it in the order and you decrement its neighbors in degree. So now it becomes 0 and it is pushed into the stack, right? So let me just clear these out. So now my 4 is the only element in the stack, and then I take this and there is no neighboring element, so that is the end of it. And you see that I have reached this state, that this is the topological order and which is correct. You can take up courses in this order. So that is about the BFS way. This algorithm is also known as Kahn's algorithm, right? Kahn's algo. Now let's talk about the DFS way, right? So in DFS way, let's draw the graph again, right? So in this, what we do, we start from the top node and make a DFS call onto its neighbors. So first I reach 2 and then I reach 4, right? This is the DFS call. So from 4, can I go anywhere? No. So I push this onto a vector or a list, whatever you like. So I'm taking a vector, right? Now my DFS call returns to 2. So do I have any nodes left in its DFS call? No. So I push 2 in. Now I go back to 1. Now can I make any further DFS calls from 1? Yes, I can. So I make a call to 3, right? So from 3 I make a DFS call to 4, but 4 is already visited. So I return back. So I come back to 3, and do I have any further nodes which are not visited? No. So I push 3 here as well, and then I make a call back to 1, and now I have no more nodes left to visit. So I push 1 as well. But you'll see that reading from this side, this is not the correct order, but it is correct order from this side. So I will reverse this vector. So what is the reverse vector? So the reverse vector is 1, 3, 2 and 4, which was the same result as we received in BFS. So yes, this is the correct answer we have reached from DFS as well. So that's the DFS way to do topological sorting. Now let's get back to the question. So for the question, you need 3 steps. The first step is that you have to make a graph, right? The second step is actually course schedule 1, course schedule 1, or if I simply say cycle detection. Cycle detection. So you can check that video out where I've discussed this thing in detail. And then finally, the third thing that you have to do is topological sorting. Right. But you'll notice that in my code, I have combined these two steps as single step, and you'll see that how efficiently and beautifully that thing works. So without wasting any time, let's move on to the code part. So this is the basic function that is given to us. In this, num courses are the total number of courses, and this is a vector of vector where we are given how these courses are related to each other. And here I've defined a vector CNT. You'll see its function when I discuss the topological sorting part. Answer here will store the final topological sorted order, right? Topological sorted order. And here this graph is actually making the graph. So you see that this is making the graph, that I've pushed the values according to their prerequisites given in this, right? And this is the function that does the main work, where it stores the answer and accordingly. So you'll see that I've sent all the courses here. So for those courses which are not prerequisites of any other courses or do not require any other prerequisite, this will accumulate for them as well, right? So that's why I'm calling it for the entire number of courses, right? And then you can see this reverse function that in the end I've reversed my answer variable. So because I am using the DFS algorithm in code. So if you remember that in the approach part, I discussed that I was returned with the value like this, whereas the correct topological order was from reverse. So this reverses that final vector and then I return that final vector. So this is the main function for it. Now let's move on to this DFS function, which will help me achieve my topological sort and my cycle detection. So this is the DFS function and it returns a Boolean value. So if it returns true, that means there is a cycle, and if it returns false, that means not a cycle. So let's discuss the parameters. So this is the answer vector which stores the final answer in reverse order, right? This is the current vector, current, which is an integer value, the current node that I'm visiting, right? This is the graph and this is CNT. So let's just discuss what this vector does. So it keeps check of two things: visited as well as in stack. So if you don't know what this in stack vector is, you should again check out course schedule 1 video where I've discussed what this means. So to brief you out, what this in stack means is that when we talk about a cycle in a directed graph, only checking if it is visited is not enough. We also need to check if it is currently in the stack as well or not. So if this in stack value is true, that means I've visited a node again whose DFS call was not completed and hence it was a cycle. So this keeps check of that when I'm visiting a node, whether it is in stack or not. So if it is not in the stack, that means it is not a cycle. However, if it is in the stack, it is a cycle. So these two lines, I'll come back to it. So first of all, what I do is that I mark count of current is equal to 1. Now this is equivalent to two statements that is to mark visited as true, right? And in stack also as true, right? And then I make a DFS call on it. And then finally, when the DFS call for this current node is ended, I make the count of cur as 2. So this is equivalent of making in stack as false, right? And then I push this current node into my answer vector, right? I'll explain this during the dry run and I return false from it, right? Return false means not a cycle, right? If this has returned true, that means it was a cycle. We'll just discuss how. So when I come here, now let's discuss here. So in the DFS call, when count of current is 1, what does it mean? That it is visited and it is in stack. So if the current node was in stack as well as it was visited, that meant that this node created a cycle. So when this value is 1, it means true, that it is a cycle and it returns true. However, when it is 2, I'm not concerned with the visited value, but it should not be in the stack. So when current is equal to true, it means that in stack is false and hence it is not a part of a cycle. So I return false here, right? So that this node is visited and is not a part of a cycle. Hence, I do not need to traverse this node again. This node is already traversed. So I can return from this state. Now let's try and dry run this code. Right. So I'm going to take the graph that I've been taking for the entirety of the video again. Right. So same graph. And let's mark it as 1, 2, 3, 4. So I start my DFS traversal at 1. Right. So I mark the count. So let's take the count vector here. Right. Let's take it for 1, 2, 3, and 4. These are not the indices. These are the nodes. Right. The value of the nodes. Right. So count of current, is it 1? No, it's empty right now. Is it 2? No, it's empty right now. So I make it as 1. Right. And then I move on to its DFS call. First of all, for 2. For 2, it returns back here. So right now it's empty. I make it as 1. For 2, I go to 4. Right. So from 4, I cannot make any further DFS calls. Right. So first of all, I've made it 1 because I encountered this statement. And since there are no connected nodes to it, I move to this statement and I make it as 2. And I push back in my answer 4. So 4 I've pushed back. Now what does this mean? That the node which is at the minimum or which is at the bottom in my DFS call will be pushed first. That means it will be taken at the end. Since I'm in the final returning, this is returned as reversed. Right? And that is true also because you can see that it must be taken at last because it is reached at last. So I push 4 and then I return false. So here I return false. So for 2, any more nodes are not left. So I make its count value as 2 and I push it back into my vector. And then again I return false. For this, 3 is left. So I'm go to 3. So for 3, first of all, this is encountered. So this is made as 1. and then I go to 4. So for 4, is current value equal to 1? No. Is current value equal to 2? Yes. So I return false from here. That means I do not need to try and traverse it again. And then I come back to 3, and then I push it as 3, and then I come back to 1. So for 1, I check here again. So for 3, when this node was made, it was made 2. Now for 1, is any node left to traverse? No. So I push it back here and I make its current value as 2, and then I return false. So you can see in my answer, I've reached this value. So the reverse of answer is 1, 3, 2, 4, which was the correct topological order. Hence, that means that my answer is correct and I have achieved the correct state. So let's try and submitting this code now. Right? So you can see the code here as well again, if there's any confusion, and you can see that it does get submitted. So yes, our algorithm is correct, and it is fairly good memory efficient and good time efficiency as well. So if you've liked the explanation today, don't forget to leave a like and subscribe to the channel and press that bell icon, since I'll be posting a lot more videos soon enough. And you can check out the entire playlist from the description below and the link to course schedule 1 and other similar questions. So thank you for joining in and thank you for your support. So keep coding and keep learning. Thank you.